Great. Thank you so much for the invitation and for coming today. So today I'm going to talk a little bit about some of the East Coast work that we've been working on, trying to bring in coastal climate information into the coast and thinking about multiple stressors within that space. So just as a little bit of background, globally, right, these variables are changing, but there's rates at which these changes are happening really varies. So here's an example on the left showing you the change in dissolved oxygen globally, the rates per decade. You'll notice that the Atlantic pretty much doesn't have any. And then on the right, you'll see sea surface temperature anomalies and the trend from Andy Pershing's paper in 2015 showing how anomalously the kind of region of the Northwest Atlantic is warming and relative to the rest of the area of the globe, in particular over this time period between 2005 and 2015. And so there's the sub-region within the Northwest Atlantic is experiencing some rapid change, especially in terms of temperature. It's also been experiencing some, hypoxia-related issues within Cape Cod Bay and some of the other coastal embayments. These new kind of events within Cape Cod Bay have happened over the past 5 summers. And some of the papers, this one led by Malcolm Scully, kind of investigating it, are finding that these like lobster kills that are associated with the hypoxia in the region are potentially driven by both the changing temperature and the changing phytoplankton groups that are being observed in the region. So kind of a change in the composition there. And so we know that there's something going on, right, in the system. Is it just temperature or is there something else, kind of driving this stuff? But what hadn't been characterized are sort of the trends of oxygen on the outer shelf itself. And so one of my students pictured there, Hung Nguyen, his paper is now in revision. So I'm working on trying to kind of bring together all the observations that we can from the World Ocean Database within the depth range. Now it's 50 to 200 meters. So sorry about that. It's 50. He started out with 50 to 100 meters, but we moved it to 50 to 200. And within that subsurface kind of depth range on the outer shelf, we're finding that the shelf region is experiencing a significant decline over the past 40 years in oxygen, and that rate is greater than the North Atlantic basin, right? And so there's some other rates that are given there in gray that some folks had worked in deeper waters, kind of thinking about kind of characterizing the changes over the shelf region. And there's notably another piece of another work that has been done in the Gulf of St. Lawrence. And so also finding a decline within that particular subregion. So with this, so now we know that oxygen is also declining on the shelf as a whole. So what's going on with the carbon variables? And then we'll get back to the why. The carbon variables have been observed to kind of to increase. So one of them is the saturation state, which I'll clarify what that is in a second. So saturation state has been thought to increase in surface waters in the Gulf of Maine over this time period where we're experiencing this rapid warming. And so that's kind of in contrast to what you might expect and what is defined as ocean acidification. So that's also, it's strange. So just to remind ourselves, kind of like for those of you who don't think about ocean acidification as much as I do, ocean acidification here is like, the process by which CO2 is absorbed by the ocean and pH is reduced, as well as carbonate ion at saturation state in kind of a predictable way. And that CO2 that's absorbed is from emissions. And so here you can see this plot that's updated as to near current of PCO2 or CO2 in the atmosphere going back from Station Mauna Loa in Hawaii to the 50s. And nearby at Station Aloha in the 80s, they began measuring in the water what was going on. And you can see that the green curve there is tracking that atmospheric CO2 increase for the most part. And then the pH, in that same location is declining. And so this is this is what ocean acidification is, right? And so, and just to define saturation state, so as that CO2 is absorbed into the water, there's a series of chemical reactions that happen where CO2 interacts with the water, and, dissociates and equilibrates with both bicarbonate and carbonate ion. And one metric of, of ocean acidification that people track is the saturation state, which tells us how close we are to the equilibrium value of 1. And if you're above that, then it's energetically favorable to produce calcium carbonate, and below that, it's energetically not favorable, and dissolution is preferred. And so that value of 1 is often one that is like looked at from a physical chemistry perspective, although organisms like the pteropods that are dissolving in the spheres there tend to feel, this threshold and have noticed impacts of this threshold far above 1. And so it's common for folks to look at values that are more species specific and often and often above 1 for the various organisms. So, so kind of going with that, on the East Coast, one of the main bivalve species that we can concern ourselves with is scallops. And so I'm showing you a picture here from some work that has like larval sea scallops, grown in a lab setting with sufficient carbonate ion versus those that are grown, in an area where, or in a tank that had insufficient or less carbonate. And, so you can just see the smoothness of the shell with the sufficient carbonate, and then the ones that are lower. So basically we start to think about this around 1.5 for juvenile calcifiers and bivalves in particular, that start to feel this threshold above that physical chemistry definition of 1. But that lower saturation state can result in less energy available for growth as well, because it is this energetic threshold. That's kind of why we care about this. So getting back to the story of the Gulf of Maine having this saturation state that's increasing, this is, sort of why this is happening. It's likely due to the change in the circulation that the region is experiencing from increased presence of Gulf Stream water in the region. And that's part of what Joe and Brewer worked out in their 2018 paper, where they kind of looked at like what would be contributing to to this trend. So here they've broken down saturation state by the other effects and then ocean acidification. So ocean acidification as the role of that increased CO2 in the atmosphere, kind of, and the equilibrating, so you can see that in blue here. And so the ocean acidification is contributing, but these other effects include temperature, the salinity trends, and the associated alkalinity trend are all contributing to in the green and kind of masking this ocean acidification signal over this time period. And similarly, pH is also affected, but not as much by these other effects. And so you can see you might be able to see the ocean acidification signal record more strongly. And this is something that we kind of know from the global OBS. So this is a paper from 2019 showing that pH is far less sensitive to sea surface temperature than saturation state is. So these are global data now. The top panel showing you in the pink the saturation state for aragonite, and the bottom panel the pH on the total scale for various latitudes on the left-hand panel, and then on the right-hand panel versus sea surface temperature. And so you can see that, the patterns across like the equatorial regions having higher saturation state at the surface and then lower as you go to the poles, with some variation around that. And that pH has more consistent, less latitudinal variability and not very strong relationship on the right-hand panels with sea surface temperature, whereas saturation state is very strongly tied to temperature changes. And this is because of the kind of carbonate chemistry and all of the equilibrium reactions that go on with kind of the buffering chemistry in the seawater. So So it makes sense then that saturation state in the surface waters would be the changes would be largely affected by the warming trends in the region. That said, we know that the subsurface waters in the benthos are already experiencing low saturation state values in the mid-Atlantic bight and also in the Gulf of Maine. And we know this from observations. And so this is one example of that from a State of the Ecosystem report in 2023. And so what you're looking at are bottom saturation state values from summer cruises that are showcased by those dots there. And within the dots are the colors. The colors indicate the bottom saturation state from those cruises. The kind of more continuous values are from glider lines, and you see Grace Saba and her team pictured there with one of the gliders that has been equipped with the ability to observe carbon variables. You can see some glider lines in the Gulf of Maine as well that University of Maine is operating that are also on this map. But the reason that there's that kind of focus on the mid-Atlantic is because that's the area where the sea scallop fishery largely resides, and within that area, also onto Georges Bank, but this is the Mid-Atlantic report, so they focus on the Mid-Atlantic. But in any case, in the zoom in, you'll see that there's some areas highlighted there in green that show that kind of regularly that region has been identified as a hotspot because it always, it seems to regularly experience these low saturation state values around 1.1. So suggesting there might be something different going on subsurface. We're challenged in terms of observing and understanding what's going on in the carbon records on the coast because they don't go back very far. There's only one in New England that is the one that Joe worked with that is at the surface. And so kind of trying to reconstruct what's happening in the subsurface, we've been relying a lot on, we've been starting to rely on these kind of empirical relationships that extend carbon values to, from other hydrographic information. So we have large data sets of oxygen, as my student Hung showed you, and temperature and salinity, right? Nitrogen, these other things, these other variables that we could use in order to extend the records back further in time. And so here's some examples from a student that worked with me and wrote a paper kind of creating some of these. And there are others that are available that are regionally specific, as well as some that are global that have been put together to basically extend these carbon records in time and space. And so if we do that at one of these time series that is in the long-term mooring that goes back a little bit further now to 2002, that's nearby the moored record that was at the surface that I showed you that was increasing from 2005 through 2015. You can see that at the subsurface from this long-term oxygen and temperature record that's there, we reconstructed what the subsurface saturation state would be doing. And it looks like it's not following what the surface is doing, that it's in fact declining at a rate that would be an order of magnitude faster than what's happening in the North Atlantic basin. And so, that means that maybe there's some process that's separating the surface from the subsurface trends, and that's something we have to consider kind of in monitoring the region kind of moving forward. Of course, what would also be helpful in extending these records are regional simulations that are well evaluated that we can also kind of try and reconstruct what's going on. And so these regional, one we've been working with as a ROM system that's been coupled to cobalt. We call it ROMS NWA. We also have one that we've been working with the regional MOM6, which I know this group has been hearing about, the regional MOM6 for the same region coupled, and I'll show you some results from that. And so this is from the 2021 paper where we worked with NWA ROMS, and you can see that same now moored time series is in black, that Salisbury and Johnson from 2015. And so this is now just a climatology showing you that that the models do a good job of recreating that simulated saturation state at the surface, the seasonal cycle of that, with the high values in the summer and the low values in the winter. What's also plotted here is a Canadian downscaled simulation for the region that they call GSBM, and that is in purple. Okay, and so we can then go back and compare the regional ROMs to the historical simulation to this A1 record to sort of see how well the ROMS model might be doing. And we can see that it's biased a bit high in terms of oxygen, but does capture the variability in the trend fairly well. And so that is exciting, something that Hung is working on. And then separate that out into the role of solubility versus AOU changes. So here AOU is the difference between the observed oxygen and what would be at saturation, and kind of is a metric that can be useful to sort of diagnose drivers. It could indicate either local biological processes or kind of circulation as important contributors to the oxygen trend. And so what we can also use this to is to further diagnose the relative contribution of solubility change driven change, so that the warming water holds less gas versus the AOU change, and it reveals that there is a positive AOU trend, and that is greater than the solubility trend, and suggests that that's what's in fact driving the oxygen down, not actually the solubility, despite the strong warming in the region. Just as like a teaser, this is from the Northwest Atlantic ROMS for the same location, and or the Northwest Atlantic MOM6, I'm sorry. So the MOM6 results, regional MOM6 that Andrew Ross led, that was recently published, and we worked with them. Like, here's some observations that Hung's been doing, observational evaluation showing that that bias is reduced and that the model does a better job even so, but the results still stand that the AOU seems to be largely the driver in the area for the historical change. So like, where would this AOU increase be coming from? So one idea is that, consistent with the circulation change that's kind of been well established in the region, that between the shift between the Labrador current and the Gulf Stream, that's been kind of well characterized by the warming. That folks analyzing the trends in the warming in the region. Actually, it also corresponds to chemical changes. So the Labrador current has a lower AOU than the Gulf Stream in particular. And so increase in Gulf Stream waters also brings more AOU to the shelf. And so that's consistent with that story as well. And I'll just point out there have been some long-term observations of the chemistry also further south, kind of where the Gulf Stream, more like kind of downstream within the Gulf Stream, right, of New England. And you can see that they did find in this paper that the oxygen was in fact declining in that Gulf Stream waters as well. So there is kind of some preconditioning going on, and the DIC, of course, is also increasing within it. So kind of bringing forward, how do we bring these changes kind of into the projections? So we've been working on doing a regional, taking this simulation then and running it into the future using the dynamically downscaled forcing that that folks at PSL who worked with Mercedes Posable-Yule, on the West Coast doing that, helped us to employ here on the East Coast. And so what we did was we used the historical, after her methods from 2022, we used this historical simulation plus the global projected change to achieve kind of localized future projections. So here, the atmosphere was forced by global reanalysis in the past, and then the delta global projected atmospheric changes were taken from the CMIP6 GFDL simulation from SSP 5.8.5, and similarly, the SOTA conditions were added the global projected ocean change from that, and then we ran a simulation continuously for 100 years. And it did this in an effort to try and help inform the coastal communities. In particular, are pictures of us with workshops in the scallop fishery. As I mentioned, that's particularly important species, and it is undergoing some changes, as you can see. So in terms of since the 90s, there's been a shift in the biomass. So moving north, there's more catch that's being brought in New England than there is in the mid-Atlantic. And so there's a lot of changes, as I talked about, that are going on. And so kind of what are the most important ones? And we have a huge multidisciplinary project team kind of working together to try and help diagnose this. And we have been doing workshops, as I showed you pictures of, with the fishing industry and trying to bring that in. So we focus on this in part because the species, not just because it's an engaged, active industry, but also because they are working with a long-lived species. So scallops live for 20 years. So that's like a really long time. And so projections out to 2100 only traverse about 4 generations from now. It also really takes a long time for adults to grow to harvest size, 4 to 5 years currently. And there's some suggestion that that timing might change kind of in the future. And then they live a complicated life cycle that's shown here from Jenny Rubin's paper, this cartoon showing you that the planktonic larvae kind of occupy the surface waters, but then once they settle, they're hanging out in the benthos, in that benthic water, in that habitat. So we've been trying to sort of figure out what is a resilient scallop fishery and sort of how do we help them to become more resilient through these changes. And doing that, we've been kind of going around the scallop shell here about quantifying the change and projecting it going forward. Locally, simulating scallop growth using a dynamic energy budget model, trying to figure out what adaptation options exist within the communities. There's a social science team working on that and examining their individual risks. We have an advisory committee and a series of workshops that we do one-on-one conversations with. And then in the end, we're trying to generate management guidance, and we kind of go back around the shell again each year. One of the important things we've figured out as part of this process, this around the shell like iterative loop, is that this trust building with the industry is really important. And so we partnered with a boundary spanning organization called the Commercial Fisheries Research Foundation, who's been also working with folks from Hui, Glenn Gaworkowitz in particular, to kind of like outfit the research the fishery with CTDs and the ability to make observations directly. So we use their observations to compare to our historical simulations in order and showed these to the fishermen in order to try and help to build trust and also to have them understand like they kind of they have a sense for how things are that they observed out there, and then kind of this connects them with the model fields and has been kind of an effective trust building tool. So then we went forth and gave them projections. So one question they kept asking us is, when should we worry about ocean acidification? And so these again are just from one RCP scenario, but gives us an idea of kind of a worst case scenario under that. And so here what we're looking at are the years when the PCO2 exceeds some critical level that's been identified by Shannon Masek at the Milford lab, and she's got papers out with her postdoc Emilian Poos about these thresholds. So on the left, you're looking at PCO2 when it's above 650 microatmospheres for more than 6 months of the year. And on the right, you're looking at the year when the saturation state is below 1.5 for more than 6 months of the year. And so the colors indicate the cooler colors indicate near now, and then the warmer colors indicate out near the end of the century. You'll also see on here on these maps the scallop rotational areas, which are important for the management areas. And so what things to note are that there's large areas of the Gulf of Maine that are experiencing some of these thresholds now, there's a lot of spatial variability in kind of where and when these conditions would emerge, but that it seems that it's more severe in the north, with the exception of that area, that hotspot area that was identified in the ecosystem status report around the Hudson River outfall. And temperature-wise, Zhoumen Chen, who's been working with us, has been working on figuring out kind of what's going on with temperature. And so temperature can also be lethal for scallops if it's above 18 degrees centigrade for some short period of time, like a few days. So here we just have, if it's that way for a month, kind of in what year you would expect that threshold to be exceeded again in that bottom waters. And what you notice is that a lot of the southern Mid-Atlantic bight and some of the shallower areas are exceeded near now, but then this doesn't really expand much in the simulation into the area where it is dominated by a feature that is important within the region called the cold pool. And so the cold pool then volume, by its traditional definition, is plotted here on the left, showing you that the total volume kind of going forward into the future, that it still persists, it gets smaller, but it's still there all the way through underneath this hammer of a forcing from SSP 5, 8.5. And so that kind of gives us a bit of hope that the cold pool persists, but it's also really interesting as to why it does and sort of what dynamics, and Juman's working on figuring that out now. This also means that there's kind of opposing drivers in this benthic habitat from the north and the south, and that could mean that there's some benthic habitat compression in this fishery's future that the managers that in this spatially managed fishery might need to consider. The last step is one of my other students is working on a dynamic energy budget model, and she's working on trying to understand how the growth rate, time to harvest and recruitment changes would be expected with these. So stay tuned for results there. So with that, I'll just conclude that if oxygen is declining, the trend is kind of driven in large part by AOU despite the observed warming, and consistent with these other climate drivers, it's influenced by this changing circulation in the region. And that despite this kind of masking of OA, that we do think large areas are going to be exposed to in the near future, and if they're not already, and that may cause some benthic habitat compression in the region. And we really need these long-term observations to evaluate those important feedbacks on these timescales and these models that are like incredibly critical. And so with that, I'll thank my funders, and if there's time, answer any questions I can.
Hi, Sam. Nice talk and great story connecting to the fishing industry. So my question is, I think towards the end of the presentation, you showed this projection of the years that the bottom temperature reached that threshold. If I were to think about this, with the expansion of the Gulf Stream and the warming of the slope sea from the subtropicals, the years when the temperature reaches the threshold, I would think it's going to be earlier at the outer shelf. But I think in the map you showed is earlier near shore. Is that right?
Yeah, I think that I know. That temperature map is very interesting, right, for many reasons. And I think that the shallow waters experience that more, it's like sooner, right? And then there must be like the presence of the front, and there's a lot to work there. Welcome to I would love to bring you into the conversation about that more and sort of work with you, sort of figure some of that out. I mean, Jimin is like figuring out some of it, but I think there's a lot of dynamics there to understand why the temperature doesn't get worse, right? Why it isn't worse, why it looks as good as it does, you know what I mean, within those projections. And so some of those features like that shelf break front and the and the cold pool are probably providing significant barriers. And the question is the simulation simulating things that we know regularly, kind of pass those barriers, like the rings and the instabilities and stuff like that, well enough in order to kind of, or do we need to do better in order to include those, events more kind of in our projections? It's a research question, right? Like That's kind true. Of in terms of it. And I think there's a lot to figure out in order to, and shows that we need these tools at these higher resolution, because those features apparently are important in creating locations, to protect and to identify resilient strategies, right? I mean,
yeah, I agree. Thanks. And also interesting to see that cold pool is providing that that barrier in terms of shielding warm temperature. Yeah, nice talk. Thanks.
Thanks.
Yeah, thanks. Awesome talk, Sam. I have a question on the number of observations. You showed a chart that is the number of observations exploded between maybe 2002 2012. And one of the U.S. Cliver PAWS panel interests is in the health of ocean observing systems. Just wondering, what is the cause for that period? Does that give you very obvious, visible advantages for study if you design ideal, coastal observing system in the future, what that system will look like.
Yeah. Yeah, I think that oxygen provides a lot of, like, because there's a lot of barriers to providing the ideal system for carbon right now because of the limitations of some of the sensors for the autonomous pathways for observing subsurface, right? That oxygen can help fill. And so I think oxygen creates a really nice example to think about biogeochemical observing optimization in the coastal waters. And that plot, when Kung made it, shocked us because there was like a decline that was so drastic. And it was like, why are we stopping observing of oxygen in this area? Please don't do that, right? Like, but he had to do a lot of sensitivities around that, as you can imagine, within his paper to kind of make sure that that wasn't contributing to the trends. And I didn't have time to kind of go into all of that, but yeah, there is a lot to dig into there. Canada plays a large role in observing. So there is also an international component to this within this area, because he did extend it into the Scotian Shelf. And it matters for this kind of water mass change, right? To sort of have the observing extend all the way around the hook. And so their observations had changed a lot during that area. But the increase was because we started observing the ECOMON surveys started happening and observing the oxygen, within the area. And so there's been some, kind of like that going on between it declined from the Canadian side and trying to bring it up on the US side. And but it hasn't reached a place yet where I think it, like it's enough, right? I guess if that makes sense.
Yeah. Yeah, thanks.
Mhm.
That's interesting.
But also having these world ocean databases where now we have it all in one place, like from, it's helpful to kind of tease that out a little bit too, right? Because before, when it wasn't centralized like that, it would be, there's other places in other regions of the world that I've been working in that it's really hard to, figure out even where the data is, you know what I mean, to start asking these kinds of questions. Yeah.
Okay, sure. So thanks, Sam. And to follow up on this observational question, in terms of what are the mechanisms that you have as a researcher or those that are working in this field in the coastal research arena, do you have for identifying what the observing needs are? And can you eliminate that for us, and how your results then translate to action on the observations?
Yeah, so I have, there's a couple of pathways. One is for OA, so it's a little bit stratified, right? Like in terms of the different stressors that I talked about. And so for OA, there's like these coastal acidification networks that are along the East Coast. They're all around the US, but there's Northeast, so NECAN, and there's MACAN, the Mid-Atlantic, within the regions that I talked about today. And both of those have working groups and write reports and kind of bring together stages of the science that kind of do some of the synthesis activities. And we've done that for OA observing in the area, and like found that there's a like significant difference between surface observing and subsurface observing, right? And I feel strong. I feel like that's probably a pattern around a lot of the U.S. coastal regions, like for OA, to sort of say that we don't have enough subsurface observing. And then I think that the other thing that I've learned is that the real-time observations are incredibly valuable, especially as a modeler, not just but also for education and outreach for folks to kind of learn about them, about what's going on in the ocean. So I guess there's a lot to say to try to keep it brief, but the access to kind of knowing what's happening. So there have been events that have been happening for the scallop industry that have had consequences recently, and we've had to try and go back and reconstruct like what we're doing rather than having observations out there that were available during these events, right? And as we go more and more into a future where those things happen, right? I think that it's really a challenge to not have a system out there that can do observing subsurface, especially in some of these regions for that, like if there's regions like that spatially within the ocean that are kind of designated as fishing zones that are closed, those are prime spots for like dedicated observing, you know? And so I think that there needs to be kind of more cross collaboration between fisheries and the ocean observing within NOAA, you know what I mean, in particular, to kind of figure out what that optimization strategy could be. And I think that, you know, the real time like gives us like something to hold our feet to the fire as we build these forecast systems out in space and time, and help the communities to build trust, you know, within that. And then the communities themselves want to help. And like those fishing communities in particular are incredibly capable of, you know, kind of, you know, observing themselves, you know, like kind of putting out a CTD. And in Cape Cod Bay, they're doing that as well with oxygen. I showed one of the maps, but it's just right when they bring it back on board, if it has access to satellite, it transmits, you know, so they don't have to do anything, you know what I mean, in terms of actually transmitting the data themselves. Like that technology exists, so it could be near real time, you know. So there's a tremendous capacity to, you know, to observe it. It's just a matter of implementing, I think. Yeah, and some of these recommendations. And carbon is hard, but oxygen is possible. Yeah.
Yeah, thanks for that. And just so everyone also knows that Sam's also on our new, she's a co-chair for our recently initiated coastal climate working group.
Yeah.
And I think some of these data issues are going to be front and center for that group as well.
Yeah.
So we can pick up some of this dialogue there.